about antipodal structure of the intersection of real flat manifolds in a complex flat manifold. Let's welcome.
Good morning, everyone. I'm very glad to be here, and I'm very happy to meet my friends again. I would like to thank the organizers, especially Professor Yonjin So, for giving me a chance to talk here. Well, let's start. Today, I'm going to talk about antipodal structure of the intersection of real flat manifolds in a complex flat manifold. This is joint work with Hiroshi Irie and Hiroyuki Tasaki. This is plan of my talk. First, I'd like to explain the works of Professor Tanaka and Tasaki on the intersection of two real forms in Hermitian symmetric spaces. First, I'd like to explain the symmetric space case. And the aim of this talk is to generalize their work to the complex flat manifolds. So in the second part, I will explain the generalized symmetric structures and antipodal set of complex flat manifold. And in the third section, I will talk about intersection of real flat manifolds in complex flat manifolds. And if I have enough time, I'd like to explain some applications. Okay. So as an introduction, let me show you a very elementary example. Let me begin with a simple example. This is a two sphere, and we consider equator here. Okay, and we take another equator in like this. Then we can find intersection point here and here. And it's easy to see that if this point is x, then the another point is minus x. That is antipodal point. So the L1 and L2. So if L1 and L2 intersect transversely, then the intersection is antipodal. Antipodal point. And moreover, the intersection number is 2. What is 2? That is a dimension of the homology group of S1. Okay. So we want to generalize this ancient example to symmetric space case, and moreover the complex flat manifolds. So S2 is a CP1, and L1 is its real form. So we can generalize this phenomena to symmetric case and complex flat manifolds. So this is a very elementary example, but please keep this example. Then you can understand what we are doing. Okay, so I'd like to explain the definition of the antipodal set of Riemannian symmetric spaces. Let M be a compact Riemannian symmetric space, and a subset of M is called antipodal set. If here the Sx is a geodesic symmetry of the of M at point X. M is now a symmetric space, so for each point there exists a geodesic symmetry, and A is called antipodal set if for any xy of A, the global geodesic symmetry at X preserved the point Y. So in this case, the geodesic symmetry at X is just reversing the geodesic. So X and minus X, the fixed point set of the global symmetry, geodesic symmetry at X is 2 points. On the other hand, geodesic symmetry at this point also fixes these 2 points. So in this case, the X and minus X, that is an antipodal set of two spheres. Okay, and we can define the other invariant of a symmetric space. That is a maximal cardinality of antipodal set of M. That is called two number, and we denote by this. And an antipodal set is said to be great antipodal set if its cardinality attains the two number. So if the cardinality is maximal, then such a antipodal set is called great. So these definitions were first given by Yen Chen and Professor Nagano. Okay, let me show you another simple example. That is, M is a symmetric space, Rpn, and we consider a subset of M, these lines, these n plus 1 lines. Then, for example, geodesic symmetry at this point is reversing the orthogonal complement. So geodesic symmetry at this point preserves all these lines. On the other hand, geodesic symmetry at this point preserves other points. So this A is an antipodal set of Rpn, and we can see that this is maximal, great antipodal set. So the two number of Rpn is n plus 1. Okay, and it's very interesting result by Professor Takeuchi. He proved that M is a symmetric R space, that is a special class of symmetric spaces. Then the two number is equal to the dimension of the homology of M. Okay, so we want to study the. We are interested in the intersection of real forms, and that can be described as an antipodal set. That is a result of the works of the Professor Tanaka and Tasaki. A connected component of a fixed point set of anti-holomorphic involutive isometry of a Kähler manifold is called real form. So real form is a fixed point set of isometry. So it's totally geodesic, and moreover, this anti-holomorphic involution. So that is a Lagrangian. So real form is a totally geodesic Lagrangian submanifolds. So in this example is a real form. For intersection of the real forms in symmetric spaces, Hermitian symmetric spaces, Tasaki and Tanaka Tasaki proved the following important results. M be a Hermitian symmetric space of compact type, and we consider two real forms. Actually, the Hermitian symmetric space in Hermitian symmetric space of compact type, the real forms were completely classified, and there exists different types of real forms in a Hermitian symmetric space. So we take two real forms, and we assume that it's intersect transversely. L1 and L2 are Lagrangian submanifold, so the intersection is a point if it's intersect transversely. Okay, and then they proved that the intersection of L1 and L2 is antipodal set of L1 and L2. Yes, in this case, real forms L1 and L2 are both of these are also symmetric spaces. So we can define the antipodal set of L1 and L2. And in addition, if we assume that L1 and L2 are congruent to each other, then the intersection is a great antipodal set. So in the simple example is RPN in CPN. That is a real form, and we assume that RPN and we replace the RPN by the action of unitary group, and we assume that the intersection is transversely. Then the intersection is this form. We can prove this one. So that was the great antipodal set of RPN. So the intersection number is n-1, and that equals to the 2 number of RPN. That equals to the dimension of homology by the result of Masaru Takeuchi. Okay, we want to generalize the symmetric. We want to generalize the result on symmetric spaces to complex Flach manifolds. So, complex Flach manifold is a very important class of compact complex manifolds, and there are many different definitions. In this talk, I would like to use this definition. Let G be a connected compact semisimple Lie group, and its adjoint we take non-zero vector from K, and we consider adjoint G orbit through H. That is a orbit of H under the adjoint G. That is submanifold in K. So we don't denote MC. So this is a homogeneous space of G, and we write G over GH. H is a stabilizer at H, and we can prove that this homogeneous space can be expressed in another coset manifold, GC divided by parabolic subgroup of GC. So complex Flach manifold admits a G invariant complex structure. Okay, and next we want to define the real Flach manifolds. So now G over K is a Riemannian symmetric space of compact type, and we consider the canonical decomposition of K, and we take non-zero vector h from P. And we take a orbit of linear isotropy representation of this symmetric space through H. That is P. That is mistake. It's P. That's real Flach manifolds. And the real Flach manifold is a homogeneous space in this form. And we can verify that the real Flach manifold is a real form of complex Flach manifold. Okay, so in the next from the next slide, I would like to define the antipodal set of complex Flach manifold. But in order to define the antipodal set, we need geodesic symmetry. But now we are working on complex Flach manifold. Complex Flach manifold is not a symmetric space in general, but it has a general symmetric space structure. It's K-symmetric space structure. So we used such K-symmetric structure to define antipodal set of complex Flach manifolds. So it's slightly technical part. I would like to devote 3 slides to define the generalized symmetric structure. Okay, we take a maximal abelian subalgebra of G containing base point H, and we define root space as a usual way, and we also define the root system of G C with respect to maximal abelian T. Then we can obtain the root space decomposition of G C in this form. Then the real algebra of isotropy subgroup GH, that is a Lie subalgebra which commutes with H, and this Lie algebra can be expressed using root system in this form, and the tangent space is a coset vector space, that is this part. So the complex Flach manifold, it's very the root system works very well to investigate complex Flach manifolds. Okay, now we decompose. Now we are thinking semi-simple Lie algebra, so we can divide root system to a irreducible root system in this, like this, and we take a fundamental system of delta, and we can take a fundamental system satisfying the following 3 conditions. This is another mistake. The first condition is alpha ij h. Yeah, this one. Sorry. So this means this fundamental system contains the H in the positive wire chamber, and each alpha ij for fixed I, that is a fundamental system of delta I, and we can by reordering we can assume that the later part is a fundamental system of this algebra, and we take the fundamental highest root of delta in this form. Then this coefficient mij is a positive integer. So we define positive integer k0 using this this coefficient. That is, k0 is defined as a maximal number of this value. So for any k equals or greater than k0, we can define k-symmetric structure on complex Flach manifold MC. So let me continue briefly. And now the fundamental roots are basis of tester, and we can take dual basis Hij, and we define Z in this form. We take sum from 1 to Qi for each J, and that is included in a maximal abelian subalgebra T, and we define Gk for K in this way. That is an element in the maximal torus. And using this Gk, we can define the automorphism of G of order K, and from this automorphism we can define the diffeomorphism of MC in this way. That is just a joint GK action. So easily we can see the GK, this diffeomorphism is order K involution, and we can also prove that H is a fixed point, isolated fixed point. So theta tilde defines a generalized symmetric structure of complex Flach manifold. And complex Flach manifold is of course homogeneous space. Now we have a symmetry at one point, but it means we can extend it for any point. So now we define the generalized symmetric structure on complex Flach manifold. And so we can define the antipodal. Now we can define the antipodal set of MC. Antipodal subset of MC is called we call antipodal set if for any x and y of A, K symmetry at x preserves y for any x and y. So this definition depends on K. But the main result of my one of main result of my talk is the antipodal set is not independent of the choice of K. And we can define the K number, so-called K number. It's a maximal cardinality of antipodal set. But in fact, this value is independent of K. For this definition, Sanchez and Professor Berunt, Consol, and Fino proved that for the complex Flach manifold, the K number is equal to the dimension of the homology of complex Flach manifold. And for real Flach manifold, it's also equal. But in this case, this value is called index number. I don't give a definition of this value, but we can define index number of real Flach manifold using this value. Okay, so now we want to know the antipodal set. For this purpose, we want to know the fixed point set by the theta k tilde. That is a k symmetry at H. But this is just a adjoint GK action. Adjoint GK action. It's a linear action. So it's a I mean this action, this theta k is a restriction of this representation. This linear map. So the fixed point set means the +1 eigenspace. So we can verify using the root system. The +1 eigenspace is equal to kh. So thus the fixed point set of theta k tilde is just the intersection of MC and kh. It means the kh was a real algebra which commutes with h. So that is by definition we can obtain this form. Consequently, we can now obtain the following proposition. For any point of MC, the fixed point set of K symmetry is given by this form. It means K symmetry at X is a set of MC which commutes with X. Okay, so yes, please have a look at the right hand side. This form is independent of K. So the left hand side, the fixed point set is depend on K, but finally we obtain it's independent of K. So the antipodal set of MC is by definition, this is a definition. So it can be expressed in this form. X and Y commutes with each other. So it's equivalent to the subspace spanned by antipodal set. That is a subspace in K. That is a abelian subalgebra. So for any antipodal set, there exists a maximal abelian subalgebra containing AR. So we can obtain the following theorem. Let A be a maximal antipodal set, maximal one. Then there exists a maximal abelian subalgebra of K, and A is an intersection of MC and maximal abelian subalgebra. So the MC is now adjoint orbit, adjoint intersection of adjoint orbit and maximal abelian. That is orbit of the wide group of K. Okay, so now we understand the antipodal set of complex Flach manifolds, and we obtain that the maximal antipodal sets, we take two maximal antipodal sets of MC. Then they are conjugate to each other by the action of G. Okay, so using now we understand the antipodal set of Flach manifold. Using this antipodal set, we want to describe the intersection of real Flach manifolds. But at this moment, we don't have a general result. But today I want to show one simple example. Now we consider Flach manifold of a sequence of subspaces in this form. Then this is a original complex Flach manifold. That can be expressed as a adjoint orbit of special unitary group in this form. And in this case, the real Flach manifold, that is a real Flach manifold is a orbit of isotropy representation of a symmetric space. So symmetric space, now we consider this symmetric space SUN over SON. That the orbit of the isotropy action of SON through this H, that is a real Flach manifold. And this real Flach manifold is a real form of complex Flach manifold. Complex Flach manifold has a complex conjugation on Cn gives a canonical anti-holomorphic involution on complex Flach manifold, and its fixed point set is real Flach manifold. So this is a real form. So now we want to describe the intersection of two real Flach manifolds in complex Flach manifold. For this purpose, I want to show you the lemma of the just a linear algebra. For we take unitary matrix U, then there exists Zi and positively oriented basis of Rn, V1 to Vn, and W1 to Wn, and which satisfies this condition. It looks like a eigenvalue and eigenvector, but slightly different. So easily we can prove this. And moreover, we define the equivalent relation on this set from 1 to n. If this Zi is coincide by plus minus, and we divide this set to an equivalent class. So we can now describe the lemma 2. Yes. Now U is a unitary matrix, and we take unit vectors of Rn, and Z is a C value. Then and we assume that U and VWZ satisfy this relation. Then there exists A from 1 to S, and V and W contains this contained in these subspaces. Okay, we using this lemma, we can prove the we can express the intersection of real Flach manifolds in complex Flach manifold. And first we describe the intersection of two real Grassmannian manifolds in complex Grassmannian manifolds. So now Fk, that is a sequence of subspace, but only one subspace. It means that is a Grassmannian manifold. So the intersection of two Grassmannian manifolds, one is a canonical one, and we replace the Grassmannian in this way, original one, and we replace the real Grassmannian by the action of U. Then the intersection can be described in this form. That is this means the intersection is each connected component is a product of Grassmannians. Okay, and first we describe the Grassmannian case, and complex Riemann manifold case, the intersection of two real Riemann manifolds, we can describe in this form. This means each subspace in this is a sequence of subspaces, and each subspace is a intersection in Grassmannians. That means we consider a projection from Riemann manifold to Grassmannian, and each subspace coincide in Grassmannian. Okay, so in this form we can obtain the following theorem. Two real Riemann manifolds intersect transversely. When these real Riemann manifolds intersect transversely, we have this one, n1 from n1 to ns is only one values. I mean, these subspaces are one-dimensional subspace. Then this Grassmannian is a point. This Grassmannian is a point. So it's a discrete intersection. So this means for you, the defined zi's are different if I and j does not coincide. And finally, we can obtain the intersection as a very, very concrete form. That is a sequence of subspaces of vi plus 1. I mean, for this u, we define the basis of Rn in this way. And this means we take first we take n plus 1 vectors from the basis, and next subspace is we take n1 plus n2 subspaces like this. So that means this intersection is an orbit of the commutation, symmetric group. That symmetric group is a Weyl group of SUN. So this intersection is nothing but the maximal antipodal set of complex Riemann manifold. So it's maximal antipodal set. Okay, so we are interested in the intersection number. That is now the intersection is a maximal antipodal set, and it coincides with the k number of complex Riemann manifold, and also index number of real Riemann manifold. That value we can compute in this way, and by the result of Sanchez and Berunt Fino console, and that is coincide with the dimension of the homology of Riemann manifolds. Okay, so now we have 10 minutes. So I would like to show you briefly the application of this work, but I apologize that now at this moment we don't have any application for complex Riemann manifolds. Just this application is just for symmetric space case. Okay, first application is a computation of Lagrangian Floer homology. Lagrangian Floer homology is a invariant defined for pair of Lagrangian submanifolds in symplectic manifolds. We consider two closed Lagrangian submanifolds in a symplectic manifold, and we assume that intersect transversely, and we define Floer chain complex in this way using J-holomorphic strip from P to Q. I mean, the J-holomorphic strip is a holomorphic map from strip to symplectic manifold. And from P to Q means from P to Q. The homomorphic strip connect these two intersections, and this means this part. That is one of the J-homomorphic strip of S2, and we defined free vector space over G2 that is generated by the intersection of two Lagrangian submanifolds. Okay, and we can define the boundary operator of this chain complex by this. And here the NPQ we count the number of the isolated J-homomorphic strip connecting P and Q, and by mod 2. So it's a G2 homology of coefficient G2. And if its difficult point is to prove this one. If the boundary operator satisfies this condition, then we can define the homology. It's called Lagrangian Floer homology in this way. And and using the antipodal structure of the intersection of two real forms, we can prove that for a monotone Hermitian symmetric space of compact type. Monotone means it's a symplectic condition, but now it's a Hermitian symmetric space. This condition can be described in it's a Kähler-Einstein manifold. So if Hermitian symmetric space is irreducible, then it's satisfied automatically. And we consider two real forms, and we assume that this sigma L1 and L2, these are minimal Maslov number of L1 and L2. But we assume that this value is equal to or greater than 3. But this condition is not so strong. The except case is just this simple example. This example, CPN in RP, CP1 and RP1. In this case, the in minimal Maslov number equals to 2, but other cases it's greater than 3. In this condition, we can prove that the Lagrangian Floer homology is generated by this one. This means that is just a Floer complex, of real forms. This means the antipodal set of intersection of two real forms in symmetric spaces is an antipodal set. So using the geodesic symmetry, we can reverse this J-homomorphic strip in this way. So this means geodesic symmetry gives a free G2 action on the moduli space of J-homomorphic strip. So if we count the isolated J-homomorphic strip, it's by mod 2. It means completely 0. So this means the boundary operator is 0 operator. So we can trivially obtain the Lagrangian Floer homology. This theorem tells us that the intersection of real forms is a least intersection number under the Hamiltonian deformation, because the Lagrangian Floer homology is invariant under the Hamiltonian deformation. And moreover, we can as a corollary, we can obtain this generalized Arnold-Giebenthal inequality. Now we assumed M is an irreducible Hermitian symmetric space. And Professor Tanaka and Tasaki completely described the intersection of two real forms in irreducible Hermitian symmetric space. Using their result, we obtained this result. The most case is this one. And first one is very exceptional case. Maybe Professor Tanaka will explain this result, details today. And okay, so intersection number is equals or greater than of minimal value of the two dimension of homology. And using that Arnold-Giebenthal inequality, we can prove the Hamiltonian volume minimizing property of some real forms in complex hyperquadratic. That is a complex hyperquadratic in CP n+1. And we, in this complex hyperquadratic, there are several types of real forms. But that is just a product of spheres divided by Z2. And the Arnold-Giebenthal inequality is an estimate of the intersection number. And we also use the integral geometry. We can estimate the volume using the intersection number. So combining these two results, we have the volume estimate of the real form under the Hamiltonian deformation. And as a corollary, we can prove that in a complex hyperquadratic, there is a totally geodesic Lagrangian sphere that is Hamiltonian volume minimizing. So by old work by Grach, Morgan, Ziller, that sphere is homologically volume minimizing when n is even case. But n is odd case. The homology is banished. Odd homology is banished. So this real form never homologically volume minimizing. So this corollary have a meaning when n is odd case. Okay, it's time, so I'll stop here. Thank you very much for your attention.
Do you have any questions?